Well, I'll say good morning to everyone. So I thought I would start out by showing the schedule for the course to remind you that on Tuesday, October 16th, we'll have an exam. It will cover the first 5 sections, and today we'll, first 5 chapters I'll call it, and today we'll finish the 5th chapter and start the 6th. But the 6th will not be covered on this first exam, just the first 5. It will be an hour and 15-minute exam. Well, it'll probably be about a 20-minute exam, but you have an hour and 15 minutes to take it in. It will be closed book, closed notes. I don't expect you to memorize a lot of equations like Zernike's. If you have to use Zernike's, I will give you the list of Zernike's. You should know that 2nd cosine theta is m lambda, and that's about it, I think, for equations. The exam will be similar to the homework problems, and if you look on the web, I think you can find the exam that I gave last time I taught this course. So any questions on the exam? Yes?
The other homework problems, problems, are those the same scale?
They're similar, yeah. I mean, I'll probably look at the other homework problems, and I probably won't give you one of those exactly, but I'll give you something similar to what the other ones are like. Maybe. Any other questions? So the next problem, I have another trip coming. I mean, that's you have a lot of faculty members who are about ready to take a trip to because of the OSA meeting. So next week, it's going to be a little strange what I'm going to do. I'm going to record Tuesday's class on Monday at 12:30, and it will be in the other classroom. And then I will give Thursday's class during the normal Tuesday time. And so it would be great if you either attend the class that I teach on Monday, or you probably can't do that. If you could watch the video before Tuesday, that'd be great. But if you don't, it's not going to be bad. I'm going to try to arrange it. So if you've not seen the class that I'll teach on Monday, it'll still be okay for the class that I'll teach on Tuesday. And so then Thursday of next week, there will not be a class given since I've given both of them. And then the Tuesday after that, we give the exam, and then the Thursday after that, I'll be back. So any questions on that?
So we'll have class on Tuesday, even though it's affiliate?
Right, we'll have the Thursday's class on Tuesday. How's that? So the normal 8 a.m. Tuesday morning I'll be here. But that will be giving class number 16, and class number 15 I'll give on Monday. Any other questions on that? Okay, wanted to go back here to a couple of things I talked about last class. So last class, when we were talking about 2-wavelength interferometry, I said what we're doing is we're taking a measurement at 1 wavelength, and then we're going to calculate the phase distribution, say, and then take a measurement at the other wavelength and calculate the phase distribution and take the difference. And I said, but this is really looking at the beat between the 2 interferograms. And then I went on to say, and I show this slide right here, and then I went on to say I really should show a moire pattern for this. But at that point, I didn't have a moire pattern for this. So since then, I have put one together for you. So I wanted to show that today. So this would be an interferogram taken measuring some mirror at a wavelength of 488 nanometers. And this mirror is going to have some spherical aberration, and we're going to have some defocus. And of course, there's a lot of tilt fringes, as you can see there. So that's measuring the mirror at 488. This is measuring the same mirror at 6328. And so if I find the difference between the two, which we can do by doing a moire pattern, what we get is something that looks like this. And if you go through the calculations of lambda 1, lambda 2 divided by lambda 1 minus lambda 2, you'll get an equivalent wavelength of 2.13 microns. Now what we could do here, I mean, we can change the tilt here simply by rotating this a little bit. And I do this more to show you that I really have two patterns here that I'm finding the moire of. Okay. So that's just another way of, hard to get back to zero there. I can get to zero, but then I take my fingers off and I move away there. Just showing you that another way of thinking about two wavelength interferometry is like a moire. Now remember, a moire, we're multiplying the two. We're not adding. If I were to just take this pattern and add to it this pattern, you don't get the beat. You have to see the multiplication of the two in order to get the difference. So any questions on that? Okay. One other thing I wanted, there were some questions after the class, and I realized it was something I was saying was confusing here, or something I was showing anyway was confusing. So this was our interference microscope where we're doing the vertical scanning, looking at the coherence function as we change the distance or the length of the test arm down here. And what was unclear about the drawing, it looks like I'm just illuminating a little bit of the surface. What I'm actually doing, though, I'm illuminating an area over the surface here. And just like up above, where we see we have the reference up above, the second plate there, the size of the reference is the same as the size of the sample that I'm looking at. So I'm not just illuminating a point, I'm illuminating an area, and then we're imaging that area up here on our detector. So we're measuring, you know, maybe it's a millimeter by a millimeter, or depending on the objective, it might be 10 millimeters by 10 millimeters. But we're measuring an area, not just a single point. Okay. Yes, there's an obscuration here because, unfortunately, I can't point from the iPad. I have to come over here. But there's an obscuration here, and that's one of the disadvantages of the Moreau. And the size of that obscuration is equal to the size of the sample that we're looking at. Later, I guess it's probably in the next chapter, chapter 6, we're going to talk about different interferometer objectives you might use in an interference microscope. But probably the most common one is the Moreau that I show here. And maybe if I go to the next drawing here, that shows the reference nicely. And so again, it's not just illuminating a point, we're illuminating an area and measuring an area at a time. Okay, any questions on that? Okay, well, let's go up to where we zip ahead here to wherever it was we left off last class. So we were looking at different samples that we could measure using this, I call it coherence probe, the vertical scanning interferometer. And we looked at a print roller here, said we could measure the pits in that. We were looking at a piece of paper and saying you can actually measure the roughness of a piece of paper. And this was another sample that I liked. This was a micro machine piece of silicon. A lot of steep slopes here, a lot of structure. Now, of course, if the slopes are so large that the light doesn't go back through the microscope objective, you're not measuring it. You have to get the light back into your microscope. And so if I looked at this, I would see, well, you see some dark areas there. Those are areas where I've just lost data because the light didn't get back into the microscope objective. And this was a binary optic lens. This was just a piece of steel or iron that had been milled. It was some chatter was present, ripples in the surface. This was a heart valve, artificial heart valve, and back in the WICO days we measured a lot of these. Now, once you get the data in the computer, there's a lot of different things you can do, and I don't know what happened somehow in going from what was on the computer to this PDF that I'm showing. I lost some of the stuff in the histograms and whatever, so you can't, that's missing. But anyway, the whole point is once you get the data in the computer, there's all kinds of analysis you can do. And I tell you, when you're selling these instruments, you think you have every analysis possible, but then every customer that comes along, they always want something you don't have. And salesmen are so good at selling things you don't have. So then you add them, then you have them. This was just a metal with some pits in it. Kind of interesting. And you always have to measure coins for some reason. I don't know, that's essential, but I never found out how to make any money measuring coins, but always you have to measure them for some reason. People expect it. Okay, well, this was an interesting project here. This had to do with the measuring of the inside of an engine block, measuring the cylinder. And the surface microstructure here is quite critical for getting better gas mileage and less pollution. And the way that people normally measure this is to use a little stylus, just a little needle that you run along the surface and you measure how that moves up and down. So it's a contact test. And you get a line scan of what the surface structure looks like. But by using an interferometer of this type, you can get much more detail. You can get area information over an area without touching it. You can generally do a lot faster than what they can do a measurement with a stylus. In the next section, I'll say a little bit more about stylus profilometers. So the system we built, maybe I'll go to the next slide and then I'll come back to this one. So what we're going to do, we have this engine here. This was a Saturn engine, if I remember right, for this particular picture anyway. And we're going to make a little microscope that goes down into the cylinder. And so this is what it was here. And so we're looking inside the cylinder, and again I show the light coming to a point, but I mean we're imaging an area. And to do the vertical scan, we would move, well, the assembly you see, we would move that up and down, and then that would move the focus point in and out, or the image point in and out. And so that's the way you would vary your path for the reference or for the test relative to the reference, and do your vertical scan. And you could do quite a good measurement here. People generally want a narrow measurement over a long ways, and so what we would actually do would be to take several measurements and then stitch them together. And you could end up with something that looks like what we have on the left here. And I forget just how many, well, it says 6, so there's 6 segments that we stitched together. And you can see the honing lines. You can see the little grooves in it. You can measure how deep they are. And you can measure the angle that these honing marks make. And that turns out to be a critical item. So the system worked very, very well on measuring these cylinder bores. But I remember back in the days when we were making these, this was not a big money maker for us, I have to confess. In fact, I think we sold one. So that was a money loser for us. And I remember one trip I made to General Motors up in Detroit where I was trying to sell this thing to them. And I remember this one engineer who was probably 55 or 60 years old saying, you know, this is really great. But he said, you know, I've been using a stylus to measure these my whole life, and I'm going to continue measuring a stylus to measure these for the rest of my life. So that was kind of the end of that sale. I think over the years they have become, they are now beginning, or more than beginning, they are using these. So the automotive companies are using something very similar to this. But it probably took 10 years of trying to sell these into that industry.
What's RZ?
That's the peak to valley. Oh, no, that's not. Our T peak to valley. RZ, you know, I can't remember right now just what that was. I'd have to. No, it's. I think it's a certain percentage of the points, but I have to go back and check that. I can't remember right now after 20 years or so. I forget just what that was. RA is the average. It'll come to me later. The other thing I remember about selling these, probably what I remember most about that trip to General Motors was that I had the computer. The computer was set up on a table, and I decided that for showing it off, I'd rather have it on this table over on the other side. And it was just a desktop computer. It wasn't bad. So I just picked it up and carried it over there and put it on the other table. And I got in tremendous trouble because I didn't have a union employee move that computer for me. So I spent the next hour or more filling out paperwork and saying I would never do such a terrible thing again. And anyway, I don't know. I couldn't work in that type of environment. This is a picture I took off the Bruker website this summer. I went up there and looked at some of their latest measurements, and I'm going to show you a few of them here. Unfortunately, there are no numbers here, so we don't know just what the heights of different colors correspond to. But again, it's looking at the cylinder bore, and you see the honing line, so on. This is a fuel cap, and again, this was made by stitching together a bunch of measurements. And what I'm going to do now is to zoom in on a portion of this and see the fine structure. And so that's really just the bottom portion of what we had here, I guess. So we had it over a large area, but we also had the fine structure here. This is another one I took off the Bruker website, just of another camshaft chatter again. They have a nice a whole collection of beautiful pictures up on their website, yes.
Just curious if it's only a coincidence that you give almost all the automotive examples how these are used. Is that the biggest industry that uses this kind of device?
Well, it's funny, it's become a very big industry. back in the days when I was running Wyco, that's where we couldn't even sell into that industry. So maybe I'm trying to show off now because it took 10 or 15 years of selling to finally get into that industry, but it's a pretty good industry to sell into now. But this is really, it's in the medical area, it's in the hard disk area, it's in the semiconductor area, it's in a lot of different manufacturing areas. It's a very versatile tool. Here's one. Cloth. I loved this picture when I saw that on the Bruker website. I don't know if they have any market in this area or if they just thought this was a pretty picture. And I don't even know just why they would, I'm not sure why there would be a market in this area, but in any case, isn't that beautiful? Okay. I think that's the last one I have, yeah. So any questions on a vertical scanning profiler? Coherence probe? Well, I think it's really cool. Not only did we sell a lot of them, and Bruker's and other people are selling a lot of them now, but it's really using technology. The optics technology is really old, the idea of white light interference. But by combining it with electronics and computers and software, it's made into just a extremely powerful tool and applications in many industries. Okay, so let's go on here to talk more about surface quality. So that could have come into this chapter as well. I put it in the other chapter because I wanted to combine it with the two wavelength and the white light stuff. But it really was measurement of surface quality. But now we're going to talk a lot more about measurement of surface quality. And we're going to talk about several techniques. The first one is just going to be viewing transmitted or reflected light. And then we'll go on, we'll talk a little bit about the stylus profilometer. We'll talk about atomic force or scanning probe microscope. Then we'll go on to some optics tests, the Leo test, the fecal interferometer, the Nomarsky, and then we'll come back to the interference microscope, but not using white light, but a more regular interference microscope. So if we talk about surface finish, what do we really mean? And typically we're talking about pits, we're talking about scratches, maybe the surface is strained, or stained, I should say, or maybe we have an incomplete or gray polish of the surface. And with the exception of this incomplete polish, most of these factors are really beauty effects. And no one wants to buy optics with a scratch on it or with a chip on it. But to be truthful, probably the optics will work well enough, even though you do have that scratch or that chip. And the only time that it really is critical, these beauty effects really are critical, is when you're near a focal plane. So you're going to see, in your final image, you're going to see that scratch or pit, whatever it is. Or, there are cases where you're especially sensitive to stray radiation. You just can't have any source of scatter. Or, in high energy laser systems, if you have a scratch or something, that hit it with a high power laser beam, you may get severe damage because of that. So in most cases, these are really just beauty effects, except for the incomplete polish, but not always. A common way of specifying surface finish is what's called scratch and dig. And this goes way back to 1954 when the Mill Standard 13830 was published, but it's still widely used today. And scratch and dig, you have two numbers you mentioned. You have an 80-50, let's say. Well, what does that mean? Well, the 80 is the apparent. So if you look at it, I mean, it's the apparent width of the scratch in microns. So that would be 80 micron scratch. And the 50, well, that's the diameter of a pit or a bubble in hundredths of a millimeter. Why they kind of mixed units here, I'll never understand. So a 50 really means 500 microns or half a millimeter. So 80-50 is scratch of 80 microns and a pit or a bubble or something of half a millimeter. So if we look here, I mean, scratch and dig numbers, as I said, they're used all the time. And what you generally do, you have the sample and you have a set of reference samples. And you compare your sample with the reference to see which references it, what number reference it matches up with. And an 80-50 is sort of an easy thing to fabricate. 60-40, that's probably the most common. That you see a 60-40 or maybe a 40-30. And I mean, sometimes you specify numbers much smaller, a 20-10, for example. You end up paying more money, of course. And that's generally used for something like a field lens or a reticle blank, something that's going to be in the image that you're looking at. Now this scratch dig has been around, as I said, for a long time. I said 1954. And a few years ago there was another standard that came out, and that's the ISO 10107, which came out, I guess, in 1996. And that will work with smaller, it will specify defects that are smaller than what was included in the original scratch dig. There was quite a nice article on this summer in OPN in the July-August issue. And I don't have a copy of this ISO standard. In fact, whenever I hear this ISO standard, I get a little ill, because I remember back a couple years ago when I was dean, I came in one morning and I had a letter from a lawyer saying that someone turned out to be Jim Burge, but someone had put up on the website this ISO standard. And if we didn't remove it immediately, they were going to sue us. And so ever since then, I haven't especially liked this ISO standard very much. But we took it down same day, and I don't know, that seemed a little strange to me. It seemed like we should be able to put, that Jim should have been able, anyway, it went along with his class, it was part of his class notes. It seems like that was okay, but the lawyers didn't like it, so I don't even have a copy of the standard. What's that?
They sell that one?
They sell it. Yeah, they sell it. I mean, they're to their point, they have to make money some way. And so if you put it up on the web and anyone can download it, they're losing sales. So I mean, legally, they certainly were right about it, but that doesn't mean it made me very happy. Or Jim either. So also in this OPN article this summer, that they showed this instrument here that had some vision software with it that would go in and measure these defects, quantify them as to the size and so on. This particular instrument, but kind of interesting, I thought. Okay, so what we're going to do now is we're going to do some easy tests. Will give us an idea, just a feeling as to how good the sample is. And so we're going to transmitted or reflected light. And there are a couple of good references on this. One is a book chapter in Applied Optics and Optical Engineering by Elson Gene Bennett and Hal Bennett. Now the Bennetts here, they have published a lot of papers over the years, and the papers are pretty old now, but they're very good papers. I think they're people that, everything they have written is something you see the article, you should read it because it's probably very, very written. It's true. Particular reference on scattering from optical surfaces. The other is a book by John Stover on optical scattering, measurement and analysis, and that's kind of the book on this particular area. John was a professor at Montana State, and then he started a company, and he actually is here in Tucson, although I don't see him very often, but he has a small company here in Tucson doing consulting work and measurements having to do with optical scattering. But anyway, John's book is a very, very good book. So the first thing we talk about is, how good of a job did we do polishing a surface? And if we didn't do a very good job polishing a surface, we will see what we call orange peel, or some people like to call it lemon peel. But the idea is you just take your sample and you illuminate it with a beam of light and a nice bright source, point source, and you look over some distance away and you'll see the reflection. And you'll see some structure. If a surface is not polished well, in this reflected light, you'll see some structure. And this structure looks like the peel of an orange or a lemon. So it's just that you have slope variations on the sample, and so that causes a redistribution of the light. We're not imaging the sample over here. I'm just looking at the reflected light. And it's going to cause a redistribution of the light, and we'll see the structure in that redistribution. And it will look like let's say like the peel of an orange. So we're getting that structure from OPD variations. And so you can look at either transmitted light, or you could look at reflected light. And the question is, which test would be more sensitive? So think here for a second. If I'm looking at reflected light, and I have a height variation of h on the sample, then the OPD in the reflected light would have a variation of 2h at normal incidence. Or if I'm doing it at some angle of incidence theta, it'd be 2h cosine theta. In any case, it'd be, at normal incidence, it'd be 2h. If I look at light transmitted through the sample, and again I have a height variation of h, transmitted through the sample, I will see an OPD, it goes as what? N minus 1 times h. And n is 1.5 or so. And so that's like a half of h. So for transmitted light, the OPD I'm getting is half of the height variation. For reflected light, I'm getting something like twice the height variation. So there's a factor of 4 difference. The reflected test will be 4 times as sensitive as the transmitted test. Okay. So you generally would look at a sample in reflection. Unless maybe if you're selling the sample, then you look at it in transmission. But if you're buying it, you look at it in reflection and make it look as bad as possible. Normally you do this in reflection. So it's a simple test. You just need a bright source, bright point source. You don't want an extended source that will smear things out, but a bright point source, and look at the transmitted or the reflected light. And you don't have real numbers as to what the surface is like, but you get kind of a little feel whether it's acceptable or not. Now, if I want to see pits in a surface, a way that is very sensitive is, say I have a piece of glass here, and if I just do edge illumination, and then I look down here, any pits on the surface will light up. So the light's just going down the edge here. I mean, it's not a very sophisticated setup, just illuminating it. And I'll see light coming out of here. It's going to light up. Any pits will light up. And then you often will compare that with standards to see if it's acceptable or not. The other approach is we take this sample and we illuminate it with a very bright light. So I illuminate it like this, and the light's reflected off that way. But if I have any pits here, that will scatter the light. And so while the direct light goes over here, if I'm just looking at this, it will light up, and I'll see the pits also. So you want that to be a very bright light, but it's a pretty sensitive test. Now, of course, a problem is if I have any dirt or dust on the sample, that will also scatter light. And so the sample has to be very clean in order to not be fooled by the dust on it, dirt on it. So we're not looking at the direct light, we're looking at the scattered light. And then the next thing, which is pretty close, is we're going to use what's called a Slaren system. So let's look at it here. So now this is the sample, and I'm illuminating the sample. Well, maybe I show a laser beam illuminating it, but it doesn't have to be a laser beam. But I'm illuminating it, and I'm putting a lens afterwards, and the light comes to focus. I'm illuminating with a collimated beam. And that lens also will image the sample over here to the right. And then what I do is I block the unscattered light. And I can block it either by putting a little stop in there, or what you normally do, you just put a razor blade in and you block one whole side here, plus the focused light. And so over on the right, the only thing I'm going to see is the scattered light. And so if I have any pits, and maybe this particular image I'm showing here is more striations in the glass, and you see some little bright spots, which are the pits we're talking about. Or maybe it's dust. Again, you have to have it very clean. You can be fooled. And you can very easily then pick out any pits on the surface or striations in the sample, as we have here, and index variations. Anything that causes the light to be scattered away from the focused beam, you'll see. And again, we're probably not putting any numbers on this. Maybe we're comparing it with a reference, or maybe we're just looking at it and kind of estimating whether it's going to be acceptable or not. So that's the Slaren system, and we'll see more pictures for that later in the chapter. So any questions on this? Has anyone done something like this? Probably has. Pretty. You do it before you know it actually has a name. It's just so logical. It's something you would do. So this takes us to BSDF, bidirectional scatter distribution functions, or BRDF, bidirectional reference distribution functions. And this is where I'm going to take some material from John Stover's book. And so we have some particle, and we're going to illuminate it with light, and it's going to scatter light. And probably just how it scatters will depend upon the polarization of the beam as well as what the particle is. But what we do is we will take a sample, like A sample, and we're going to illuminate it with some light, and that's from the left. power, scattered light as a function of angle. And so you see the P naught, so that would be the direct beam. That's the specular beam coming on. And then we have the, D P sub S at the top here. Doing the scattered light per solid angle, the function of angle. And we have what we call the BRDF, the bidirectional reflection distribution function, which is defined here. Well, we're illuminating the sample with some irradiance, which is in watts per unit area, and we're measuring the scattered light scattered through a solid angle per unit illuminated surface area. And then, so that's the ratios that we have there for the BRDF. And then we put in, well, sometimes, not all, but sometimes, often anyway, we put in a cosine factor to, it's a cosine of the angle that you're looking at the scattered light at, to adjust the illuminated area to the apparent size when you're viewing from some other angle. So that would be the definition of BRDF. And so what you do, you have some instrument like this, and you may be looking at the scattered light, or you may be looking at the reflected light here. That out. Who was probably the world's expert on measuring BRDF and BSDF. And he used to have all kinds of equipment for measuring scattered light at all different wavelengths and all different angles. In fact, if you know where the football practice field is, you probably don't even know. You don't know where the football field is, probably to begin with, but there's a football practice field over here. And there used to be where that football practice field is, there used to be a Jewish temple there. But by the time I came out to Arizona, it was not used as a Jewish temple anymore. It was used as an optical sciences laboratory. And that's where Bill Wolf used to have all of his rooms and rooms filled with his scattering equipment here. So if we have a constant, we call that a Lambertian surface. So that means that the scattered power per unit solid angle falls off as a cosine. And so this BRDF, then the cosines will drop out here, and the BRDF will be a constant here of, well, I say 1 over pi, but it's actually whatever the reflectivity of the sample is divided by pi. And so Bill used to use different samples to try to simulate Lambertian surfaces, like sandpaper, things like that, try to get as close as possible to a perfect Lambertian surface. You could measure, so that was measuring scattering as a function of angle. You could measure total integrated scatter. So here we have a sample, and the sample is surrounded by a sphere. So you illuminate the sample, and you have a small hole in this sphere, both to get light in and to get the direct reflected beam out. And then all the other light that is reflected off that sample will strike this sphere, and that will image this light back onto the detector. So the detector is seeing all of the scattered light, and so they call this total integrated scatter. And the TIS goes as 4 pi times sigma of the surface divided by the wavelength. And then if you don't illuminate at normal incidence, you'll put in a cosine of the angle of incidence. And if you square that, if I look at that, I mean, what I see there, remember when we talked about Strehl ratio, and we said, well, Strehl ratio went as 1 minus the RMS squared. And if I think here for a second, that's really just the RMS squared, what I have there, or the effective RMS, because of cosine theta, angle of incidence. We'd have 2 pi over lambda times sigma, but because the reflection is 2 sigma. And so that's really just the 1 minus RMS squared from the Strehl ratio. That's just that RMS squared factor here. So that would be our total integrated scatter. And the Bennett's were big people in measuring total integrated scatter. Okay, mechanical probes, stylus, profilometers. So here's a picture again I took from the Bruker website. So what we're doing in a stylus instrument is we're taking we're rubbing that over the surface. So I used to say this was like a phonograph record, but you're too young to know what phonograph records are. Anyway, maybe you do know. Anyway, we're taking this stylus and we're rubbing it over the surface, and it's moving up and down depending on the height variations of the sample. And we're going to very precisely measure how this thing moves up and down, and from that we're going to measure surface roughness. Now, I always thought this was a terrible idea, and when I got into using interferometry to measure surface roughness, I intended to put all these people out of business. But I have to admit that here we are 30 years later, and they're still selling a lot of stylus instruments. And it's probably gotten a lot better over the years. But if you don't adjust it right, I mean, you can scratch a surface, you can damage a surface. But it really, I mean, it has amazingly good height resolution. I talk here about a vertical resolution of an angstrom. I mean, that's what Bruker says on their website, but that's, I mean, I've read a lot of papers that, I mean, they really do get vertical resolution of an angstrom, which I always find amazing. And if they don't adjust it right, they can damage the surface, certainly, by scratching it. But if it's used properly, it actually is very good. Yes.
Do they use a beam reflection off the stylus arm to keep track of that movement, or how do you?
That's one approach, and we'll use that coming up for the AFM. But typically, with this instrument, they don't. They have some transducer that's measuring. So it's a magnet inside of a coil, and they're measuring. As this magnet moves up and down, it generates an electric signal, and from that they're measuring how much it moves. That's probably the most common way of doing it.
And that beats the optical method?
I don't know if it beats it. We're going to use the optical method when we go to the AFM. The AFM is going to be better accuracy in this. I think it's less expensive maybe. And it's just, I don't know. It's been very well developed over the years. Maybe it's more history is the reason they do that. I don't know. I mean, I say, why in the world would anyone use a mechanical probe like this when you can use an interferometer? Well, I can give you one example. If you say you're looking at something where you have different materials, And if I'm using light, if I'm using an interferometer, I'll get different phase changes on reflections from the different materials. And so if I'm measuring some structure that has dissimilar materials across it, using interferometry, I can get incorrect results because of the because of the phase change on reflection. And you don't have that problem here. Another case, if you have thin films, using interferometry, you get all kinds of strange phases, and that can cause trouble. And here, you just, if you have a thin film on top, you're measuring the top surface, and you're not getting false measurements because of phase changes due to the thin films. And so there really is a very good market for something like this. And I was pretty naive when I thought interferometry would put this type of measurement out of business. So I took this off the Bruker website. Bruker has the old, what I thought of as Weichel, the old company I had. They have the optical measurements. They have the AFM from the company Digital Instruments, and they have the stylus here from what used to be called Sloan. And so they have all three of these types of measurements, and so it's a very nice website to look at. And so this is, again, they don't put any numbers on here, which bothers me a little bit. But anyway, this is looking at some machine part, I guess, using the stylus. I don't know, just another sample. I thought, another pretty picture, I thought. Okay, any questions on the stylus here?
Those pictures, when you're running a stylus across the surface, you get just like a line profile.
You get a line profile, and then you do it many times.
Oh, they just interpolated that?
You just repeat it. I mean, it's slower. That's where, again, when optics came along, I was going to put them out of business because you're measuring an area at a time. It's much faster. In fact, back in when we introduced our interference microscopes, the stylus people were just doing single lines, and I think we kind of forced them to do areas to compete with us. But so now they would spend the time to do scan after scan after scan, and the speeds are certainly faster than they used to be.
I was just wondering how, historically, how long has the stylus approach been a practical method of
Forever. I don't know. If I go back, the first paper, the first reference I saw where they could do angstrom type measurement was by Gene Bennett, and that dates back to about the late 70s, early 80s, that they were doing angstrom. Now, when she was doing originally, I mean, it was very difficult, and now machines have gotten much better, so they can. It doesn't take a Gene Bennett to do that type of a measurement anymore. The styluses date way back. I don't know. I think if you go back into the 40s, 1940s or so, you'll see them too. I mean, they've improved a tremendous amount over the years, but it's been around a long time. And now I'm convinced it's going to be around a long time in the future. Something that's pretty similar to that in many ways is what we'll call the atomic force microscope or scanning probe microscope. And with this system, we're actually going to measure down into the angstrom, sub-angstrom range. And so here we have a very sharp tip. We'll see a picture of one in a second that is theoretically not touching the surface. it's feeling the atomic force between the tip and the sample. And what we're going to do here is we are going to use a laser to read this out, reflect a laser beam off of it up onto a photodiode array. And if that cantilever moves up and down, then a spot across the photodiode array will change. And so what they typically do here, they put the sample on a PZT and they move the sample up and down to always keep the cantilever at the same position. And then they read out the voltage that's applied to the PZT, and from that they know how far they've moved the sample. And so they're not measuring, unlike in the stylus instrument, they're actually measuring how this needle moves up and down. Here they're moving how the sample moves up and down to keep a constant force between the cantilever tip and the sample. And so I just say it has a very sharp tip. We'll see a picture in a minute. And it's made out of silicon or silicon nitride with a radius of curvature that's in the nanometer range. And so you're looking at the forces between the tip and the sample, and that will lead to deflection of the cantilever. And then, as I say, the typical way of reading out here is to use a laser spot reflected off the top surface of the cantilever into an array of photodiodes. And this is looking at the tip here. The whole width here, I guess, is 100 microns. Very, very sharp. And this is again off the Bruker website of just showing one of their instruments. Has anyone here used an AFM? One here in optical sciences?
No, I used it at my old university.
Okay. Okay. So what are your thoughts about using an AFM?
I thought it was a tremendous amount of fun just because it was such high precision.
Oh, it's incredible.
For me at the time.
Yeah.
Also kind of difficult to get some pretty bad scans if you're not really careful.
Well, you have to be careful. You don't want to crash your tip into the sample. But it's an amazing instrument. What it can measure. This was looking at again from the Bruker website, looking at a 20 micron by 20 micron glass sample. So if that's 20 microns across there, you can see what really fine detail you're seeing. Oh, I couldn't resist showing this. Back in the Wyco days, we built an AFM, so this goes back 20 years ago. And I'll just show some results from the AFM that we built. Again, that was looking at a glass sample. So, I mean, this is not maybe so surprising, but it does surprise people. Of course, the RMS you measure on a sample depends upon your lateral resolution. And so you say, well, customers will say, why, you're using your microscope system and you're getting a certain RMS, and you're using the AFM, you're getting a different RMS. I mean, which one is right? They're probably both right. It's just that you're looking at different special frequencies. If you're using an optical system where you're resolving lateral dimensions down to a little order of the wavelength of light, and here where you can get down much, much smaller than that. And so the glass sample probably will look rougher, or it may anyway, look rougher using an AFM than what it looks using an optical system. And just another glass sample here. This was a magnetic hard disk. This was kind of interesting to look at. So these are the colors are in angstroms, and the lateral dimensions are in nanometers, I guess. Looking at integrated circuit. Oh, this is my favorite one. This is looking at blood. And it's my favorite one because it's my blood that we're looking at here. I have no idea what that's saying about my blood, but I always like this picture. Okay, so AFM stylus are somewhat alike, although we'll say with the stylus we're touching the surface. With AFM, ideally we're not touching the surface, but we're awfully close. Very easy to touch. The stylus has very good vertical resolution, has pretty good lateral resolution. It will. It's not confused by different materials. It's not confused by thin films, but it's slow and it's pretty easy to damage the surface using a stylus. AFM is an incredible device that can measure in the sub-angstrom range with incredible lateral resolution, and is just super. But maybe if I had a complaint about it, it's a little slow and maybe a little hard to operate, although they've gotten much easier. So now what I want to do is go and talk about different optical techniques for measurement of surface structure. And the first one we're going to talk about here is what I call the Leo test, although it's the same thing as what you call the Zernike phase contrast test. And I don't know what the history is on this and why it has both names. Zernike got the Nobel Prize for doing this, but Leo came along someplace and got his name on it too. So what we're going to do here, we're going to take a source, and initially I'll start with a point source, although later I may change that, make it a little larger. And I'm going to illuminate a sample, and I'm going to look at the light reflected off the sample, and this light will come to focus, and I'm going to put in a mask there, and we're going to talk about just what that mask is. And then I'm going to go to where the sample is imaged and look at what we see in the image. And what we're going to do is we're going to get some intensity or irradiance variations across the image of the sample, and we're going to relate that back to height variations on the sample. And I think for the derivation I go through, I do it for normal incidence. If we're illuminating something other than normal incidence, and the height that we measure is not z, but is z cosine theta, theta being the angle of incidence. So the mask we're going to make is, it's going to have an intensity transmittance of little a squared for the region within the first dark ring of the airy disk. And then outside the first dark ring of the airy disk, it's going to transmit essentially 100%. But, and the other thing we're going to do is that we're going to change the phase of the light in this region where we have the intensity transmittance of a squared, or amplitude transmittance of a. We're going to change the phase of it by either 90 degrees, in which case we'll call it positive contrast. We'll see why we say that in a minute. Or we're going to change it by 270 degrees, minus 90 degrees, which we'll call negative contrast. And this system is going to be good only if the height variation is very small. We are typically going to use a Leo test or phase contrast, Zernike phase contrast, for heights that are a small fraction of a wavelength of the light used. And if I'm at normal incidence, then I can say, well, what's reflected, I can, if it's reflects 100%, I can say, well, what's reflected is e to the I 2 pi over lambda times 2z. If I'm not at normal incidence, it would be 2z cosine theta. And I'm saying that z is small, z compared to lambda is small, and so I can expand e to the I 2 pi over lambda 2z as 1 plus 2 pi over lambda 2z times I. And z is, of course, a function of position on the sample, so z is a function of x and y. Okay. So then I think, well, you know, this, the 1 here represents what's not scattered outside the airy disk, and the other is what's outside the airy disk. And so what I can write here, if I have unit magnification and I have positive contrast, so I'm changing the phase of the unscattered light by I can say that what I'm ending up with is an intensity distribution that's, you know, some number out in front that I don't care about, T naught squared, times AI. So the amplitude transmission inside the airy disk was A, and I changed the phase by 90 degrees, so that gives me the I. And then I have the 4 pi. I have the 4 pi over lambda z times I. And so I simply square that to get the intensity. And when I square it, I remember that z over lambda is well, I'll just say I'm going to square it. So the I here is in both terms, so I can take the I outside, and and just square that. And and I can take the A outside if I want to. So I get a T naught A squared times 1 plus 4 pi z over lambda A. And I said that z over lambda was small, so z squared over lambda squared is even smaller. And as long as A is not too small, I can just write that as 1 plus 8 pi z over lambda A. So I have an intensity here that if z over lambda A is small enough, I have an intensity here that is a constant plus something that's proportional to z. Okay. And so I can make a table here. Well, first off, I say, you know, the radiance is linear to height variations related to that. And so I can make a table here of A. I'm going to put different values of A. And I also relate A to density, but maybe that's not too important. And I look at an example here where Z is 10 angstroms and the wavelength is 633 nanometers. And so I have a table here that shows that as a function of A, a 10 angstrom height will change the intensity by 4% if A is 1, 7% if A is 0.56, 13% if A is 0.32, and so on. Now, in order to get this linear relationship, when I squared this, I had to assume that the z over lambda A was small enough that I could neglect the term that went as z squared over lambda A squared. And if that's not true, then if A becomes too small, then that's no longer the case. And so I show another row here where I don't assume that z over lambda A is so small that I ignore the z squared over lambda A squared term. And so I would get, instead of 1.22 for an A of 0.18, I get a 1.24, and for A of 0.1, I'll get a 1.44 instead of 1.4. But the point that I'm making here, the real point, is that for a height variation of only 10 angstroms, we can get, 4, 13, 22, 40% change in the intensity. So it's a pretty sensitive measurement of height variations. Any questions before I go on? Well, this technique has been used a lot over the years. And what you often do is, instead of using a point source, you'll use an extended source. And maybe the extended source is this angular region that we see right here. And then what we have to do, we illuminate the sample, same as before, but now our little element that we put in is not just something that where the mask matches the center portion of the airy disk. Now we make it so the mask matches the geometrical image of the source. So if this was an angular source here, the mask is going to have to be an angular source there. And so this way we can get more light. And so this would be a more common way of using the phase contrast microscope. Okay. And I think that's the end. Oh no, I show some pictures here, I guess. So these are some results. This was a pitch polished lens surface. And I got these from the Atlas of Optical Phenomena. Did we talk about that before? No, okay. So several times during this course, I'm going to show pictures that I take from this, either volume 1 or volume 2 of this Atlas of Optical Phenomena. Was written by some professors from the Institut des Optiques in France. And both volumes are quite thin volumes, but they're just filled with some beautiful, beautiful pictures. And we used to have volume 1 in our library here, but I think it disappeared years ago. But fortunately, before it disappeared, I scanned all the pictures, so I have them all. Volume 2, I actually have a copy of that at home. I bought volume 2, and I'll tell you, when I bought volume 2, I gave $40 for it. I remember that, because that was so much money to pay for a book, $40. I couldn't believe it. Now, you probably can't believe you pay $40 for a book either, but for a different reason. Anyway, I've had that book a long time, and it was one of my best investments, I guess I'd have to say. Anyway, you're going to see many pictures during this course from this book, and this is one here. Here's another one, and in here, what we're doing is that mask A is going to be 0. It's going to, we're blocking the light. And so that's really the extreme of the Zernike phase contrast microscope, Leo test, going to the Slering method. So anyway, I see my time is up here, and so we'll start at this point for the next class. Now remember, the next class, Tuesday, I'm actually teaching on Monday, and on Tuesday we'll have the Thursday class. Anyway, I explained all that at the beginning. So if any of you can come to the 12:30 class on Monday, that would be great. Otherwise, if you can't make it, and I think it's going to be in the other room, if you can't make it, you can watch it on the web. So, old homework to pick up.